All right, welcome. Today, we're going to pull back the curtain on a seriously powerful math shortcut that can take a monster of an algebra problem and turn it into something you can solve in seconds. Let's dive in. So just take a look at this. X plus y to the power of 10. How would you even start? I mean, sure, you could write out x plus y 10 times and start multiplying, but you'd probably run out of paper, patience, or both. There has to be a better way, right? Okay, so let's dial it back a bit. Start with something we all know. We all had to memorize this in algebra class, right? A plus b squared is a squared plus 2ab plus b squared. Easy enough. But what happens when you just bump it up by 1 to the power of 3? Suddenly, you're multiplying the whole thing by itself 3 times, and you get this, a cubed plus 3a squared b and so on. It works, yeah, but you can feel it getting tedious already. Now imagine trying to do this for the power of 10. No way. And this is what we call the expansion problem. When we see boring, repetitive work like this, our brains are literally wired to hunt for a shortcut. And let me tell you, a good rule in math is that wherever you find total drudgery, there's usually a really beautiful, elegant solution hiding somewhere nearby. Okay, so let's actually lay out the first few expansions and just stare at them. Let's see what pops out. Seriously, take a second. Do you see any patterns jumping out at you? In the letters, the little numbers, the big numbers, anything? All right, a couple of patterns probably jump out right away. First, look at the A's. Their powers just march down perfectly, from n all the way to 0. And the B's? They do the complete opposite, climbing right up from 0 to n. And here's the cool part that ties it all together. For any single piece of the puzzle, any term, the two exponents always add up to n. Okay, so that's awesome. We've cracked the code for the variables and their powers. That's half the battle. But what about those big numbers out front, the coefficients? That last row has 1, 4, 6, 4, 1. Like, where are those coming from? It seems random, but it's not. Well, this little mystery leads us to one of the most famous and honestly most beautiful patterns in all of math. The secret to those numbers is hiding in plain sight inside this incredibly simple triangle. So if we just get rid of all the letters, the A's and B's, and only look at the coefficients, this is what we see. And this beautiful thing is called Pascal's triangle. Each row gives you the magic numbers, the coefficients, for a certain power, starting with n equals 0 way up at the top. But here's the best part, it is ridiculously easy to build. Okay, so how do you make the next row? Easy. You always start with a 1 and you always end with a 1. Then, to get any other number in the row, you just find the two numbers right above it and add them together. That's it. You just keep doing that all the way across. It's so simple, it's brilliant. And now we can see just how powerful this is. Just by following that simple rule, we can create the next row for n equals 6, which turns out to be 1, 6, 15, 20, 15, 6, 1. And boom, just like that, with zero tedious multiplication, we know the entire expansion of a plus b to the 6th power. It's like a cheat code for algebra, for real. Okay, so Pascal's triangle is amazing. We can all agree on that. But it's got a problem. It's fantastic for small powers, like 6 or 7. But what about that first problem we looked at, to the power of 10? Or what if you needed like the 50th row, or the 100th? You'd have to write out 100 rows of this triangle. That's not a shortcut anymore. We need a way to jump straight to the row we need. And that brings us to the main event, a formula that can calculate the coefficients for any power, no matter how ridiculously big, without needing any of the rows before it. This, my friends, is the binomial theorem. Okay, before we get to the big formula, we need one quick building block. It's called a factorial. You write it as a number with an exclamation point, like n. And all it means is you multiply that number by every whole number all the way down to 1. So 5 factorial is just 5 times 4 times 3 times 2 times 1. Oh, and there's one weird special case. 0 factorial is just defined as 1. Just trust me on that one, we'll need it. Okay, you ready? Here it is. Whoa. Yeah, I know, it looks like a monster. But don't worry, let's break it down. It's actually simpler than it looks. Look, it's got the same patterns we already figured out. The powers of A go down, the powers of B go up. The only new bit is that complicated-looking fraction at the beginning of each term. That's the part that uses factorials to calculate the coefficient to find the number from Pascal's triangle directly. This thing is the engine that lets us jump to any row we want. You know, the best way to really get a formula is to just use it. Let's get our hands dirty. So let's try it on something a little trickier than just a and b. How about this one? 2x minus 3y to the power of 5. Now our a and b terms are a bit beefier.
All right, let's just break this down piece by piece. So our n is obviously 5, our a term is the whole 2x, and, this is super important, don't miss this, our b term is negative 3y. You have to take the sign with it. From here, it's just the patterns we already know. The coefficients, we can just yoink those from the fifth row of Pascal's triangle. 1, 5, 10, 10, 5, 1. Easy. Then we just line up the powers of 2x going down from 5 and the powers of negative 3y going up from 0. See? Same pattern.
Okay, so after you do all the number crunching and carefully simplify every single term, this is what you get. And look at this. See how the signs flip back and forth? Positive, negative, positive, negative. That happens because our b term was negative. When you raise a negative number to an even power, it becomes positive. When you raise it to an odd power, it stays negative. The theorem just handles all of that automatically. It's perfect. So, being able to expand the whole thing is amazing for sure. But the binomial theorem has one more trick up its sleeve, and honestly, it might be the coolest one. What if you didn't care about the whole long answer? What if you just wanted to know, say, the 8th term? Just one specific term buried in the middle of that mess. Well, guess what? There's a formula for that. This little beauty lets you perform surgical strikes. You can pinpoint and calculate any single term you want without doing any of the other work. That first chunk with the factorials, that's what calculates the exact coefficient from Pascal's triangle. The rest is just the same power pattern we've been using all along. This is the ultimate shortcut. All right, let's put this new superpower to the test. Let's find the 8th term in the expansion of 2x minus y to the 10th power. Now think about that. Manually multiplying this out 10 times, it would take forever. And just to find one little term somewhere in the middle, forget it. I mean, this slide really says it all, doesn't it? On the left, you've got the long, messy, brute force way. And on the right, you've got our clean, elegant formula. We just plug in our numbers. N is 10, A is 2x, B is negative y. Now, here's the one tricky bit. For the 8th term, the R value we use is 7. It's always one less than the term number you're looking for. So you plug all that in, you work out the factorial part to get your coefficient, you calculate the powers, and you're there. The answer is negative 960 x cubed y to the 7th. What would have taken ages, we just did in, 20 seconds? And that, right there, is the whole point. The binomial theorem isn't just some random formula to memorize. It's a totally different way to look at a problem. It's about trading in hours of mind-numbing multiplication for just a few lines of smart, elegant calculation. It's about finding the hidden pattern. It really makes you wonder, doesn't it? I mean, if a shortcut this clever is hiding inside something as basic as multiplication, what other incredible secrets are just sitting there, hiding in the math we use every day? What else are we all still doing the hard way just because we haven't found the pattern yet?